Alright, example 3 is more complicated. Alright, so I've got 3 times x squared times y cubed plus 3 times the natural log of x times y. Alright, and again, it's always more complicated when we're multiplying higher degree functions, and throwing in a logarithm or exponential always makes it more trickier. Alright, so we take the derivative with respect to x. And again, both parts have x's in it, so I have to take the derivative of both. But remember, it's the x part that I'm looking at. Alright. And so the first function, so I'm looking at my 3x squared y cubed. The 3 is a constant, and the y cubed part is being held constant. Even though it has a cube on it, it'd be like taking 2 cubed, which is 8, 8 staying constant. Alright, even though it's 2 and I'm cubing it, it's still a constant. Alright, even though y is unknown, but for whatever point I'm picking, that y value that's being cubed is being held constant. And so the 3 comes along and the y cubed comes along. The part I'm taking the derivative of is the x part. Alright, so again, the 3 and the y cubed are constant multipliers that come along. I take the derivative of x squared with respect to x, because x is the variable that's changing. Well, x squared is a 2x. That's how x squared changes when x changes. Alright, so there's the first piece. And I'll clean it up in the next, I'll rewrite it and multiply it out in the next, when I write it out next. Alright, so the next part. Alright, so I've got a 3 times the natural log. So again, 3 is a constant multiplier, it comes along. The derivative of the natural log is 1 over whatever's inside. So 1 over x times y times the derivative of what's inside. So I'm just looking at the x times y. I've already taken care of the natural log, the outside function part. What's the derivative of x times y with respect to x? Well, the derivative of just x is 1. Y is a constant, so it's y times 1, which is just y. And then I'll clean it up. So I'm going to multiply this and move it up here. So I get my 3 times 2x, which will give me 6xy cubed. Plus here, the y will reduce, right? Y divided by y is 1. And then I can rewrite that as 3 over x. Just to write it simplified as one fraction. Right, there's the derivative with respect to y. Or sorry, x. Alright, so there's the derivative with respect to x. Now the derivative with respect to y. Well, again, I have to take the derivative with respect to y, and there's y in both functions. And so the y cubed in here and the y inside my natural log. And so it's the y I'm looking at, it's the y that's changing. X is being held constant, so it's the y part I take the derivative of, x just comes along. It's a multiplier, 0 out if there's no y with it. So in the first one, the 3 is a constant, it comes along. The x squared is a constant, it comes along. The part I'm taking the derivative of is the y cubed, so how is y cubed changing with respect to y? Well, it changes by 3 times y squared. Right, that's its derivative with respect to y. The second part is 3 is a constant multiplier. I take the derivative of my natural log with respect to y. The first part's exactly the same, 1 over what's inside. Natural log doesn't matter if I'm looking at x or y. It's 1 over what's inside. The part that matters is the inside part. So again, I've taken care of the natural log. Now I'm looking at the inside. I'm taking the derivative of the inside with respect to y. So what's the derivative of x times y with respect to y? Well, the derivative of just y is 1. X is a constant that's going to come along, so it's going to be x times 1, and so this just simplifies to x. And then if I rewrite it, cleaning it up, so I'm going to multiply this 3 times this 3, so I get 9x squared y squared plus this x and this x will reduce, right? X divided by x is 1. So I'm left with a y down here, and then I'm going to multiply out the 3, so I get 3 divided by y. And there's the derivative with respect to y. 9x squared, y squared. Let's do the next example, which is so this is a logarithm example. My next example is an exponential example. Alright, and this one actually one is harder than the other. Alright, so this is an example of one variable is much harder than the other variable. Alright, and so this one actually is a tricky one. So the derivative with respect to x first. Right, and that's the hard case. You'll notice how many x values are listed there. There are two x values. There's two x functions. There's the x times y squared, and then there's the e raised to the 2x. What are those functions doing? Well, they're being multiplied, right? It's x times y squared times e to the 2x. So that means this is going to require my product rule with respect to x, right? There's two functions and they're multiplying. And so my xy squared would be my first function. The e to the 2x would be my second function. All right, so it's my first times the derivative of the second. So again, I'm only looking at the e to the 2x with respect to x. Well, e to the 2x is e to the 2x times 2. There's the derivative with respect to x. Then plus the second, e to the 2x, times the derivative of the first with respect to x. So now I'm looking at the first function, taking its derivative with respect to x. Well, the derivative of x is 1. The y part is a constant multiplier, right? It's 1 times y squared. And so the y squared comes along. All right, then I factor. My rule of thumb, you could pull out the y squared if you wanted to, and the e term. So you can pull those out. Factor them. Actually, I'd probably pull the y squared out first. Y squared e to the 2x times 2x plus 1, right? If I pull everything out, there's still a 1 left over. And that's probably as simplified as I would go. Alright, so that was the derivative in terms of x. So the x required the product rule, because there are two x values. What about the y direction? How many y expressions do you see there? There's only the one y, right? That's it. Just the y squared is it. It's only one y term. X is just a constant, and the e to the 2x is just a constant, right? If I were at a point, and I'm picking the point 1, 1, 1 doesn't change, and then if I plug 1 into the e term, it'd be e squared, which again is a constant. And so the x parts, even though they're ugly x parts, both of them are just constants. And so the x comes along as a constant multiplier, and the whole term e to the 2x comes along as a constant multiplier. The part I take the derivative of, the change that I'm looking at, is the change in my y squared. Well, how does y squared change? What's the derivative of y squared? Well, the derivative of y squared is 2y. And it's fine if you leave it like that. It's a little more proper to rewrite it in the front, 2xy e to the 2x, but again, that's a minor thing. It's up to, I would accept either expression is fine. All right, we'll stop there. Those are the two harder cases, and then we'll get into the next examples in the next video.